Hi, Doc V. This is Alex Rippel doing the Teach the Doc assignment for molecules. And so I'm going to start with SiI4. So we're going to start by doing the loose dot diagram with silicon in the center. And it's going to have 4 iodines around the outside. 1, 2, 3, and 4. So these 4 iodines, first off, silicon has 4 valence electrons. And since there's 4 outside atoms, we're going to do 1, 2, 3, 4 valence electrons there. And looks like iodine has 7 valence electrons. And so we're going to have 1 to match each of the silicon ones. And then on each iodine, there's going to be 6 more to make 7 total. So there's 1, and then 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And this makes up the 7 valence electrons that iodine has to begin with. So for the bonding, there's the 4 bonds right here between silicon and each of the iodines, which means that there's 1, 2, 3, 4 bond pairs. And on the central atom, which is silicon, there are no lone pairs. So, yeah, no lone pairs. So there's 0 lone pairs on the central atom. This is going to be type A for silicon, and then B4 for the 4 iodines. And there's no lone pairs as we put over here, which means there's no E. Shape, we're going to look at this chart here. Seems like there are 4 outside atoms, but there's no lone pairs, so it's going to be tetrahedral. And for polarity, silicon is silicon is more electronegative than iodine, which means the arrows are going to point like this, and so on and so forth, which means that because there's no lone pairs, that means that it's perfectly symmetrical. So the polarity is non-polar. Moving on to the next one in the next video. This is video number 2. Now we're going to be doing SBr6. So we're going to start with a loose dot, and sulfur is in the middle. So I'm going to go over here. So sulfur, and there's going to be 6 bromines. And sulfur has 6 valence electrons. 1, 2, 3, 4, 5, 6. 1 matches each bromine. For bromine has 7 valence electrons. So each one's going to have 1 to match the sulfur electrons. And then it's going to have 6 more to make a total of 7 valence electrons per bromine. Like so. So I'm drawing I have 7 on each bromine. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Just like this, I have 7 on each bromine. And then I'm going to bond the sulfur electrons and the bromine electrons. Now there's a total of 6 bond pairs, so 6 BP. There are no leftover electrons. There's no lone pairs, so 0 LP. And the type is going to be A for the sulfur, B6 for the 6 bromines, and there's no lone pairs, and so it has to be 0. There's no E. For the shape, we're going to look over here. So there's going to have to be 6 X's, so 1, 2, 3, 4, 5, 6 in this one, and there's no lone pairs, so it's octahedral. octahedral. For polarity, sulfur is less electronegative than bromine, so it's going to go, the arrows are going to go out like this. And there's no lone pairs, which means that this is symmetrical, so it is non-polar. Now to video 3. Doc, this is Alex again. This is video number 3. We're going to go with ICl5. And so we're going to start with the Lewis dot. So we have an iodine atom in the middle, so a little I. And we're going to have 5 chlorines. So 1, 2, 3, 4, 5 chlorines. Now, iodine has 7 valence electrons. So 1, 2, 3, 4, 5 to match each of the chlorines, and then we're gonna have 2 extra right here. I'm gonna circle that because that's gonna be a lone pair. Now, for the chlorines, they also have 7. So there's gonna be 1 to match the iodine electron, and then there's gonna be 6 more. So it's 7 total. So I'm gonna do the same thing for the rest of the chlorines. So they each have 7. 1, 2, 3, 4, 5, 6, 7, and so on. Gonna bond the matching ones together. Yeah. All right. So now that's 1, 2, 3, 4, 5 bond pairs. There's 1 pair of electrons left over on the central atom, so that means that there's 1 lone pair. For type, we're going to have A for the iodine, B5 for the 5 chlorines, and we're going to have E1 because we have 1 lone pair. Yeah, so if we look at this chart, we're looking for 5 X's. So like this one, 1, 2, 3, 4, 5, and we're looking for 1 lone pair, and we're in the 1 lone pair, so yeah, it must be square pyramid. Right, square pyramid. And then if we look back, we can see that there's actually, so because of that lone pair, it is polar. All right, now to video 4. This is video number 4. We're gonna do XeS3. All right, we're gonna start with our Lewis dot diagram. So there's gonna be Xe, so that's xenon, and then 3 sulfurs. So xenon has 8 valence electrons. 2, 3, 4, 5, 6, 7, 8. And sulfur has 6. So we're gonna make 2 to match the xenon ones. And then on each sulfur, we're gonna add 4 more to make 6. So 1, 2, 3, 4, 5, 6 total. So now each sulfur has 6. And so we're going to connect these bonds. So now xenon has 1, 2, 3, 4, 5, 6 bond pairs and 1 lone pair. So 6 bond pairs and 1 lone pair. Now, so that's what our diagram looks like. So we have an A for the xenon, B3 for the 3 sulfurs, and then E1 for the 1 lone pair. If we look at our shapes, we're looking for 1 lone pair, and it's gonna have 3 X's. So we're looking at a trigonal pyramid. And it has a lone pair, which means it is polar because it's not symmetrical. Not a video. Right, this is video 5. We're doing CO2. So if we do our Lewis dot diagram, C is the central atom, so carbon. We're going to have 2 oxygens, 1 and 2. So carbon has 4 valence electrons. I'm going to go 1, 2, 3, 4. Oxygen has 6 valence electrons, which is why I had the 4 range like this. So 1, 2, 3, 4, 5, 6 so 6 for each oxygen atom. And now we're going to connect the bond pairs. So we have 4 bond pairs. If you look, there are no leftover electrons, which means there are 0 lone pairs on the central atom. For type, we're going to go A for the carbon, and then B2 for the 2 oxygens. No E, because there's no lone pairs. If you look at our charts, the shape, we're looking for 0 lone pairs and 2 X's, which is linear. So we have a linear shape. For polarity, it's symmetrical, and they're pulling out like this because carbon is less electronegative than oxygen. So, this means that it is non-polar. Non-polar. Now to video 6. This is Alex again, and we're now on video 6 with NBr3. So, for a loose dot diagram, nitrogen is going to be the central atom. I'm going to draw nitrogen, and we're going to have 3 bromines. So, 1, 2, 3 bromines. Nitrogen has 5 valence electrons. Bromine has 7. So I think there's just going to be, we're just going to use 1 electron per bromine from the nitrogen, like this. And then bromine is going to, each bromine has a total of 7 valence electrons. So we're going to draw 1, 2, 3, 4, 5, 6. So that this has 7 total. 1, 2, 3, 4, 5, 6, 7 total. 1, 2, 3, 4, 5, 6, 7. And now if we go back to the nitrogen, it actually has 5 valence electrons, so we're going to do 2 more down here. So yeah, nitrogen's got that 5, which means there's 1 lone pair right there. And as you can see here, there are 1, 2, 3 bond pairs, so 3, and there's 1 lone pair on the central atom. The type is going to be A for the nitrogen, B3 for the 3 bromines, and E1 because we have 1 lone pair. Type, if we look here, we're looking in the 1 lone pair and 3 X's. So that is a trigonal pyramid. Trigonal pyramid. And because it has a lone pair, we know that it is polar. Now to video 7. Video 7, we're going to be covering BeBr2. Okay, so we're going to start with beryllium as our central atom. Draw beryllium. And we have 2 bromines. So 1 and 2. Now beryllium only has 2 valence electrons. So 1, 2. Bromine has 7 that wants to get 8, so there's 1 there to match the beryllium electrons, and then there's 6 more to have 7 total valence electrons. Same thing over here. And now there are 2 bond pairs like this. Which the bromines follows the rule of 8. So that means that there's 2 bond pairs, no lone pairs, so 0 lone pairs. And the type is going to be A for the beryllium, B2 for the 2 bromines, and no E because there's no lone pairs. There's no lone pairs and 2 X's, so this is the linear shape. And there's no lone pairs, and beryllium is less electronegative than bromine, so the arrows go out like this. There's equal force, so it's symmetrical, so it's non-polar. Now to video 8. This is video 8, and we're going to cover SnF2. So our central atom here is tin, so that's going to go in the middle. And we have 2 fluorines, 1 and 2. So tin has 4 valence electrons, and fluorine has 7 valence electrons. So because fluorine, they each have 7 like this. Tin, it's going to have 1 to match this so that they follow the rule of 8, and there's going to be 2 left over. So it's 1 lone pair. So 2 bond pairs and 1 lone pair. Like that. The type is going to be A, B2, E1, because there's 1 tin, 2 fluorines, and there's 1 lone pair. If you look at our table, the type for this is right here. There's 2 X's and 1 lone pair, which means the type is angular, also known as bent. Now, for the polarity, we have a lone pair, and because there's a lone pair, it has to be polar. All right, now to video on the other side of the paper for video number 9. We're going to start with GES2. Okay, so germanium is our central atom, so we're going to go to the Lewis dot diagram. We're going to have GE in the center, and we're going to have 2 sulfurs on the outside. So 1, 2 sulfurs. So we're going to have, so germanium has 4 valence electrons, so I'm going to do it like that. Sulfur has 6. The reason I drew the germanium ones like this is because sulfur has 6. They're going to want to complete like so to get 8. So yeah, this follows the rule of 8. Rule of 8. Germanium has no leftover valence electrons, which means there's no lone pairs. So 1, 2, 3, 4 bond pairs, and no lone pairs in the central atom. So 0. Now we're going to go to our type. Our type is going to be A for the germanium, B2 for the 2 sulfurs, and there's no E because there's no lone pairs. Shape, it's going to be linear because there's no lone pairs, and there's X and X, 2 X's, so it's linear. And if you look here, germanium is less electronegative than sulfur. So the arrows go out like that. There's equal force, which means it's symmetrical. So it is nonpolar. Out of video 10. Next up is, for video 10, is AsH3. So we're going to have arsenic as our central atom. I'm going to do it a little bit to the right to save space. So arsenic in the center, and we're going to have 1, 2, 3 hydrogens. Okay, so the arsenic has 5 valence electrons, so 1, 2, 3 for each of the hydrogens. I'm going to have 2 on the outside, and then hydrogen has 1 valence electron each, so like that, which means there's 3 bond pairs, and there's 1 lone pair. So 1, 2, 3 bond pairs, 1 lone pair, 3, 1 lone pair in the central atom. Okay, our type is going to be A for arsenic, and then B3 for the 3 hydrogens, and then E1 for our 1 lone pair. If we look at our graph here, we're looking for 3 X's and 1, so 1, 2, 3, and 1 lone pair. So it is a trigonal pyramid. Trigonal pyramid. All right, now with that said, there is a lone pair, which means it is polar. All right, now to video 11. This is the 11th video for the 11th molecule, which is CH2I2. All right, so we're going to start with carbon as our central atom. So carbon is going to go right here. And I'm going to have H, I. Carbon has 4 valence electrons, so I'm going to arrange them like this for the 4 outside atoms. And so hydrogen has 1 valence electron each, so they're going to go like that. And iodine has 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We're going to connect the bonds like that. Now we have 1, 2, 3, 4 bond pairs. No lone pairs on the central atom, so 0. For the type, we're going to have A, and then B4, because we have 4 outside ones, and no E. For the shape, we're going to have, if I look over here, no lone pair, and 4 X's is tetrahedral shape. Now, for polarity, I'm not sure because there's no lone pairs. However, like the pole, like, I don't know. There's uneven poles from these two as there is to these two. So I'm going to say this is polar because one of the two has like they have 2 different poles on the carbon. So Like if you're thinking of it as a tug of war, then like it's not even. So polar. All right, now for the next video. So now for the 12th video, we have TeF6. So we're gonna start with our Lewis dot diagram. Te is tellurium. So we have one tellurium right here. And we're gonna have 6 fluorines. So 1, 2, 3, 4, 5, 6. 6 fluorines. Okay, so tellurium has 6 valence electrons, so that's going to be 1 for each fluorine. And fluorine has 7 valence electrons, so that's perfect for completing the rule of 8. So I'm going to draw 7 on each fluorine, like so. All right, now I'm going to connect the bonds. And tellurium has used up all its valence electrons, so there's no lone pairs in the central atom. And it looks like there's 1, 2, 3, 4, 5, 6 bond pairs. So 6 bond pairs. Type is going to be A for the tellurium, B6 for the 6 fluorines. As you can see here, 6 fluorines. And yeah, there's going to be no E because there's no lone pairs. So now if we look over our chart, we're going to look for the no lone pair column. And 1, 2, 3, 4, 5, 6. So this one looks pretty similar to ours. And we're going to say that's octahedral. So that's our shape. Our shape is octahedral. For the polarity, there's no lone pairs. Oh, yeah. So fluorine is the most electronegative element, which means the pole's going out like that for each one. So, yeah, it's nonpolar. On to the next video. All right, now for our 13th video, we're going to go with PCl5. So it looks like phosphorus is our central atom here. So there's going to be a P for phosphorus. And we're going to have 5 chlorines around the outside. So 1, 2, 3, 4. Wait, I couldn't do that funky. I'm going to erase it. Okay. 1, 2, 3, 4, 5. Yep, 5 chlorines, 1 phosphorus. Now, phosphorus has 5 valence electrons. So 1, 2, 3, 4, 5, 1 for each of the outside electron, or outside atoms. And chlorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7, and that satisfies the rule of 8. So we're going to do that for all of them, adding 7. 1, 2, 3, 4, 5, 6, 7, like so. All right, now each of the chlorines has 7, and the phosphorus is 5. Now we're going to connect these bonds, and turns out that we have 5 bond pairs, no lone pairs. Yeah, and then our type is going to be A for the phosphorus, B5 for the 5 chlorines, and there's no E because there's no lone pairs in the central atom. Now, if we go to our shape, we're looking for 5 X's and no lone pairs. So 0 lone pair, and 1, 2, 3, 4, 5 X's. So this is ours. Looks like it's a trigonal bipyramid. Trigonal bipyramid. Makes sense. Now for polarity, there's no lone pairs. Phosphorus is less electronegative than chlorine, so the arrows are going out like that for each atom, so it's out. And that's symmetrical, so it's nonpolar. All right, on to the next video. All right, our 14th video is going to be XeO3. So we're going to start with xenon as our, xenon as our central atom. And we're going to have 3 oxygens, like that. Xenon has 8 valence electrons. And oxygen has 6, so there's going to be 2 for each oxygen to satisfy the rule of 8. That's 1, 2, 3, 4, 5, 6. And so xenon is 8, so we got to add 2 more right there. Oxygen has 6 total, like that. So I'm going to add 6 to each oxygen atom. 2, 3, 4, 5, 6. Now we're going to make these bond pairs. And it looks like we have 1 lone pair. So that is 1, 2, 3, 4, 5, 6 bond pairs and 1 lone pair. So if we go over here, our type is going to be A for xenon, B3 for oxygen, and E1 because we have a lone pair. If we go to our shapes, our shape is going to be in the 1 lone pair column, and we have 3 X's for the 3 oxygen. So 1, 2, 3, 1 lone pair. Looks like we have a trigonal pyramid. And then for polarity, we have 1 lone pair, which means it has to be polar. All right, now to the 15th. Okay, this is our last and 15th video, and we're going to be doing molecule XeF2. So it looks like xenon is our central atom. If you look here, it's kind of a bit erased because I already did this, but my phone died while I was recording, so doing this one again. And we have 2 fluorines. And xenon has 8 valence electrons, and I know that fluorine has 7, so fluorine they only need 1 more, so xenon's going to give 1 to each fluorine, because it only needs 1 more to create 8, so it's the rule of 8. Xenon has 1, 2, 3, 4, 5, 6 left over, because that's the 1, 2, 3, 4, 5, 6, 7, 8 total that it has. So 8 valence electrons for xenon, 7 for each of the fluorines. Now we're going to make these 2 bonds, and it looks like we have 1, 2, 3 lone pairs. So we have 2 bonds, 3 lone pairs. Now, that means that our type is going to be A for the xenon, B2 for the 2 fluorines, and we're going to have E3 for the 1, 2, 3 lone pairs. Now, if we look at our chart over here, it's going to be in the 3 lone pairs column, and this one has 2 X's, which is what we're looking for, and that's 1, 2, 3 lone pairs. So this is it. It is linear. Yeah, linear. Okay, so because it has 3 lone pairs, that means it's not symmetrical, which means it is polar. All right, that is the last of the videos, and that's the end of this assignment. So, see ya, Doc.